Okay, well, let's get into this. So now that we know what an acid is and a base is, well, let's get into how this works in the context of human physiology. So just to review, remember about 1880, Arrhenius kind of came up with a definition, and based on that definition in the late 1800s, an equation was created by Henderson and Hasselbalch independently. And then Bronsted and Lowry came along in the early 1920s, and they further refined that, and that's kind of the definition, that refined definition of acids and bases that we use. Anything that donates protons is an acid when dissolved in water. Anything that accepts protons is a base when dissolved in water. And then it really wasn't until the late 1940s into the 1950s that physicians begin to use the concept of Bronsted-Lowry in the context of human physiology, right? So it's a fairly contemporary development using the concept of acid-base to measure something about what's going on with people, or to figure out what's going on with people. And based on all of this, right, the pH, and we just defined what the pH is, right? It's a logarithmic scale that represents the hydrogen ion concentration, and what exactly means is debatable, but maybe the potential of hydrogen or something like that. So the pH is primarily a function of two variables in human physiology. We know what pH literally is, right? And how we literally measure it, or we get to it. But what two major variables primarily impact pH in the human body? Well, they include the carbon dioxide concentration in your body and the bicarbonate concentration. And bicarbonate is a base because it is able to accept protons, right?
Carbon dioxide and what?
So carbon dioxide and bicarbonate are the primary factors that determine pH in the human body, right? So I just kind of drew a pyramid here, pH, and it is a function of CO2 and bicarbonate. And do you see these little brackets that I put around bicarbonate? That just means molar concentration. Anytime you see brackets, that just means we're talking about the molar concentration of it. Okay, you guys okay with that? And it should come as no surprise later on in the day when we start talking about determining the acid-base status of your patient. What are the three things that we primarily look at? The pH, the CO2, and the bicarb, right? And this comes out of the work that was done prior to this. So I think a good question, first of all, we all understand how bicarbonate plays into the picture, right? Well, bicarbonate is literally a base. It can literally accept protons. So that makes sense, but CO2? So if I look at so PA just means the pressure of carbon dioxide in the arteries, right? Anytime in physiology you see a little a, that means arterial, right? And then a P is pressure, so it's the pressure of arterial carbon dioxide. So the question is, how in the hell is CO2 an acid? Is there a hydrogen anywhere in CO2? You guys see a hydrogen anywhere in the chemical composition of CO2? Anywhere in there. So how can it be that CO2 can donate a proton, can be an acid? How is that even possible?
It has to be dissolved in.
There you go.
Fluid, right?
Yeah. How does most of the CO2 get transported in the body? In the blood, right? About 70% of all the carbon dioxide in your body is transported in the blood. Well, we know that is CO2 a polar or a nonpolar molecule? Is it polar?
Yes.
We look at it here. So if we look at C, all right. So it's flat, it's a nice linear. What do you think?
This is carbon dioxide.
That's CO2, right? So there's a carbon in the middle, double bonds, two oxygens. It's a nice flat molecule. Does that look like a very polar kind of molecule to you? No, it's not, right? It's not. The charge is spread out more or less evenly. It's distributed more or less evenly. So carbon dioxide is a nonpolar molecule. Well, what does that mean regarding its ability to dissolve in water? Because that's mainly what blood is, right? It's, you know, a little over half of it's water, right? So what do you think?
Dissolve easily.
Does it dissolve easily in water? Because what kind of molecule is water, remind me? Is it a polar or a nonpolar molecule? Polar, it's a very polar molecule, right? And what kinds of things
So
dissolve
it's
in?
not polar than-
There you go, right? Polar things need to dissolve in polar molecules. So CO2 is nonpolar, which means it doesn't dissolve in water. Does that make sense? It doesn't dissolve in water very well. So what happens is the body converts carbon dioxide into something that can dissolve in water. All right, so I drew this equation up here for you. So here I have the tissues over here on the left. I have the blood here in the middle, and I have the alveoli of the lungs on the right. So what do we have in the tissues? Well, we have carbon dioxide coming out of the Krebs cycle, right? It's a waste product because all the little hydrogens are being tore off of the pyruvate as it works its way through the Krebs cycle. And so I have a lot of carbon and oxygen left behind that produces CO2. So what happens is carbon dioxide combines with water, so CO2 plus H2O, and there is an enzyme in the body that catalyzes this chemical reaction and is known as carbonic anhydrase. Carbonic anhydrase. So CO2 combines with H2O to produce a new molecule, H2CO3. You guys see that there? Now, H2CO3 is a very unstable molecule. It doesn't tend to stay in that form. It tends to break down, particularly when it's dissolved in water, right? And this H2CO3 is referred to as carbonic acid. And acid has a tendency to break down into hydrogen ions and bicarbonate ions. Well, let me ask you a question. Will hydrogen ions and bicarbonate ions dissolve in water?
Yes.
Yeah, they're ions, right? They're charged. They're definitely going to dissolve. And so what happens is the CO2 gets converted into something that will dissolve in the bloodstream, right? And in the process of that conversion, what happens? Well, hydrogen ions are produced. Does that make sense? So carbon dioxide is converted into an acid. Does that make sense? And the reason it's converted into an acid is it wouldn't dissolve in the blood otherwise, or very small amounts of it would dissolve, and your body wouldn't be able to get rid of it. And then what happens is the hydrogen ions and the bicarbonate ions are transported to the alveoli, and when they get to the alveoli, carbonic anhydrase is present again. Carbonic anhydrase. And the carbonic anhydrase catalyzes, right, the hydrogen ions and the bicarbonate ions recombine to form carbonic acid, and then the carbonic acid will break back down into carbon dioxide and water, and the CO2 is then free to leave and get exhaled, right? And the CO2 goes into the alveoli and then it gets exhaled. Does that make sense? And that's about 75% of all the carbon dioxide in the body ultimately gets transported in this way. Does that make sense? A very small amount of it is actually able to dissolve in the blood because it is not very soluble in blood. Okay? You guys okay with that? Okay, so that's why CO2 is an acid, and that's why people say it is an acid, because it's not literally an acid, but it's converted into an acid. Okay, so that also gives rise to another discussion. And that is a discussion about the two major types of acids that we run into. All right? And the two major types of acids that we run into are what we call strong acids and weak acids. And so a strong acid is something that when dissolved in water, it dissociates completely.
That's a strong acid.
That is a strong acid. So here I have an example of HCl, right? That's also known as hydrochloric acid. Do you guys see that there? And when that hydrochloric acid gets dissolved in water, 100% of those hydrochloric acid molecules will dissociate into hydrogen ions and chloride ions. Do you see that there? And do you see this little arrow here? And do you see how that arrow moves in one direction? That means an irreversible chemical reaction, right? That's what makes a strong acid a strong acid, is 100% of the molecules will dissociate. You guys okay with that? Now, there are some examples of strong acids, hydrochloric acid, hydrofluoric acid, sulfuric acid, right? They tend to be very strong. But most acids are not strong. That is to say, when you dissolve that acid in blood plasma, not all of it will dissociate. Does that make sense? And if less than 100% of it dissociates, it's what's called a weak acid. And so here I have an example of carbonic acid here. Do you guys see that there? H2CO3. And when H2CO3 gets dissolved in water, some of it will dissociate into hydrogen ions and some of it will dissociate into bicarbonate ions, right? But the opposite can also happen. The hydrogen ions and the bicarbonate ions can combine to reform carbonic acid, right? So this chemical reaction moves in both ways, right? In the right direction and the left direction. Do you see the two arrows, right? That's what we call a reversible reaction, okay? Does that make sense? And so what happens is when I dissolve this weak acid, right, carbonic acid, acetic acid, many of the organic acids that you can think about in the body are weak acids, like lactic acid, pyruvic acid, acetic acid. Most of these are weak acids. They do not completely dissociate when they dissolve in the blood plasma. And so what can happen is, depending on the environment within your body, more or less of that acid will dissociate, will actually do what an acid does. Does that make sense? And so what happens is, if I have blood plasma and I dissolve a certain amount of carbonic acid in there, all right, a certain amount of it's going to dissociate, and what will happen is, if I let it sit for a little while, an equilibrium will be reached, right? And that's what these arrows, right? There is a certain number of times that the hydrogen ion and the bicarbonate will combine to form carbonic acid, and a certain amount of carbonic acid is breaking down into hydrogen ions and bicarbonate ions. Does that make sense? And there's an equilibrium will be reached if you kind of let the system kind of stay. So what we do to figure out how strong or how weak a weak acid is we calculate something called the dissociation constant, right? And this is referred to as the Ka. The Ka, when you see this in the formulas that I'm going to be using, and we're not really going to talk about it much, but that's the Ka, that is the dissociation constant. And what we do is we take a solution to figure out the Ka of some weak acid. We take a solution of water, of pure water, generally. Okay, this is really hard to do in human beings, but we take pure water, distilled water, and then we dissolve a certain amount of a weak acid in there, right? And then we measure. Now, what happens with a weak acid is the original form of that weak acid is undissociated. And remember, dissociated just means to break up, right? To break up into hydrogen ions or whatever. You guys okay with that? The symbol for An undissociated acid, an acid in its undissociated form, is an HA with brackets around it because we're talking about molar concentrations. You guys good with that? So what's going to happen is that undissociated acid is going to, some percent of it, right, some amount of it is going to break down into hydrogen ions and something else. All right, so when an acid breaks down, it breaks down into two parts, basically, right? It breaks down into its acid, which is the hydrogen ion. And because that hydrogen ion is positive, that means that it leaves its electron behind, right? Does that make sense? And whatever gets left behind is negatively charged, right? Does that make sense? Because it takes the electron, right? So when we talk about carbonic acid, H2CO3, carbonic acid can break down into hydrogen ions and bicarbonate ions, HCO3 minus, right? So here's one of the hydrogens there, there's one of the hydrogens there, and then the CO and 3. So everything's accounted for, right? And so what happened was when this dissociated, it dissociated into a hydrogen ion, right? This is what we call the acid, or in this case, the dissociated acid. You guys see that there? And then because the electron was left behind on the other part of the molecule, right, there, this is referred to as the conjugate base. So weak acids tend to dissociate into a dissociated acid and a conjugate base. So the reason that this is a base is, could the hydrogen ion recombine with the bicarbonate to form H2CO3 again? So could this accept the hydrogen? Yes, right? This bicarbonate could. Now it won't always, right? But it could in the environment that this is in will dictate what's going on there. You guys okay with that? So the symbol for a dissociated acid in these formulas is an H plus with brackets around it. You guys okay with that? And then the symbol for the conjugate base is an A minus, right, with brackets around it. And the A just means anion. You guys okay with that? And all organic acids, when they dissociate, will break down into a conjugate acid and a conjugate base. For example, lactic acid, right? Lactic acid, you guys have all heard of this. Lactic acid, when it dissociates, it will break down into a hydrogen ion, and it will also break down into a conjugate base. And the conjugate base that lactic acid breaks down into is something called lactate. Lactate. So when organic acids break down, their name tends to change, right? So lactic acid breaks down into a hydrogen ion in its conjugate base form, lactate. Does that make sense? Let's see if we could think of some other examples of organic acids. Acetic acid, right, that's vinegar, breaks down into a hydrogen ion and its conjugate base known as, so acetic acid breaks down into, well, lactic acid is lactate, so acetic acid is going to be acetate. Makes sense, right? Makes sense what's going on? You guys okay with that? Okay, cool. All right. Excellent. So, to figure out the dissociation constant, what we do is we dissolve a certain amount of weak acid in water, right? And then what we do is, this is the formula that we run. So we dissolve it, and then we wait for equilibrium to be reached. And then we need to know what is the conjugate base concentration, the A minus, what is the hydrogen ion concentration, right, H plus, and then what is the concentration of undissociated acid, HA, right? And what you do is you take the HA, or you take the anion, the conjugate base, multiplied by the hydrogen ion concentration, and then divide that by the undissociated acid concentration, the concentration of molecule that didn't break down. Does that make sense? So in the case of carbonic acid, what we would do is we would dissolve the carbonic acid a certain amount, a molar amount, in a liter of water, say, and then we would measure, well, after equilibrium's met, we'd measure, okay, what is the concentration of bicarbonate, and multiply that by the concentration of hydrogen ions, and then whatever that number is divided by the concentration of the carbonic acid, right? How much is left over? And then the number that comes out from doing that math, and you guys are not going to have to do this, right? You're not going to have to do this. But whatever that number is the Ka value, is the dissociation constant of that weak acid. Now, we don't have to do this with strong acids. Why? Because 100% of a strong acid is going to do what? It's going to dissociate, right? So when I put, a mole of hydrochloric acid in a liter of water, right, and then I wait for that reaction to happen, I'm not going to have any HCl left, right? This is going to be 0, right? So it doesn't. This just doesn't even matter. Okay. So this dissociation constant refers to weak acids. Are you guys okay with that? Okay. So now that we have some foundation, let's actually take a look at this equation, right, that is used to determine the pH in the human body, in human body plasma, all right? This is known as the Henderson-Hasselbalch equation. This is the fundamental equation of acid, really of acid base, of understanding acid base in the human body, okay? So, Henderson-Hasselbalch equation states the pH, okay, equals the pKa, and we're going to talk about what pKa is, okay? The pH equals pKa plus the log base 10 of A minus divided by HA. And remember what A minus is. A minus is what? The conjugate base of a weak acid, right? And HA is what? The undissociated form. You guys okay with that? Okay? So that's what pH equals, or that's how we get to pH. All right? So what I need to do is I need to convince you that this is somehow related to this. So what did we say? We said pH is primarily a function of carbon dioxide in the body and bicarbonate in the body. You guys okay with that? Good with that? Okay. So somehow I need to get from here to here. I need to connect these two somehow. So the first thing that I want to do is I want to talk about the pKa. The pKa is nothing more than the log, or actually the negative log base 10 of the Ka. You guys okay with that? So whatever this Ka value is, and again, I'm not going to make you all calculate the Ka value. There it is. But just know that it's a little p, so pKa equals the negative log base 10 of the Ka value. Are you guys okay with that? You good? Okay. So pH equals pKa, which is the negative log of the Ka. You guys okay with that? So here's a question. It has to, and the Ka is a dissociation constant of some weak acid, right? You guys okay with that? So let me ask you, what is the substantial weak acid in the human body? Yeah, what's the substantial weak acid that we deal with in the human body?
Like stomach acid?
Well, Again, plasma. We're talking about blood plasma here.
Say lactic.
Well, what did we say? pH is primarily a function of what? What two things? CO2 and bicarb. So what's going to be the primary? CO2, right? All right. So, but what did we say? CO2 is primarily what? It's primarily converted into carbonic acid, right? So to know this pKa is referring to what? The carbonic acid. Does that make sense? So we have to find the Ka of carbonic acid first, right? And then we take the log base 10 of that Ka. I don't want you to do the math on that. I'm just going to give it to you, okay? Yeah, you all right? You all right? Okay. The pKa in human plasma, right, is generally 6.1. Now, I could have just put the formula up and put 6.1 in there. But I like, well, where did that come from? Right? Oh, it's a constant. Well, where did that come from? Right? So I wanted to give you guys this foundation so you understand where this is coming from, right? So 6.1 is the pKa value of carbonic acid. Does that make sense where that comes from? Okay. So pKa plus log base 10 of A minus divided by HA. So I'm rewriting this formula. So far, so good? Okay, so let's figure out what these are, right? Because I need to put some numbers in here, right? So let me ask you a question. A minus is what again?
Conjugate base.
The conjugate base, right? And what we're really talking about here is we're talking about what? We're talking about the conjugate base of carbonic acid, right? CO2. And then HA is what? The undissociated form, right? H2CO3 or what in H2CO3 carbonic acid, right? Ultimately, carbonic acid is made of carbon dioxide, right? CO2 and H2O. You guys okay with that? Okay. So let's see if we can rewrite this equation yet again. So what we do is we go, okay, well, we got the pH down, equals 6.1, we know what that is, plus the log base 10 of, let's fill in the blanks up here and down here. So what is A minus going to be? What thing represents A minus? HCO3. You guys good with that? Oh my God, this is amazing. It's starting to make sense, right? This is so cool. So let me ask you a question. What is the normal bicarbonate in the human body? The normal bicarbonate in the human body.
The base, the normal base.
Yeah, the normal bicarbonate value. So when we measure it, when we draw a sample of arterial blood, right, and we measure it, I'm going to give it to you. The absolute normal is 24 milliequivalents per liter. That is perfectly normal bicarbonate. So what I'm going to do is I'm going to stick 24 in here. 24 milliequivalents per liter. And that is the bicarbonate value. That's the normal bicarbonate value in the human body. Are you guys good with that? Yes? All right. So let's move down to this HA now. HA is going to be what? It's undissociated acid, carbonic acid, and in the human body, what is a thing that we can measure that is indicative of carbonic acid levels? CO2. That's easier to measure than carbonic acid, right? Because carbonic acid breaks down, makes up, it's really dynamic, right? In the human body, the human body is not just some a liter of water where there's not a lot going on, right? So you can't just add something and then wait for equilibrium to happen in the human body because human body resists that. That's the whole point of homeostasis, right? Is to resist that. So rather what we can do is we look at CO2 levels, right? Does that make sense? Now, CO2 is measured as a pressure. It's a pressure of dissolved gas. And the normal P little a, remember what little a means? Artery. So the pressure of arterial carbon dioxide, the absolute normal CO2 is 40 millimeters of mercury. You guys okay with that? 40 millimeters of mercury. So what I'm going to do is I'm going to put 40 millimeters of mercury here. You guys see that there? 40 millimeters of mercury. And then what I have to do is I have to use something called Henry's law. All right? I have to use something called Henry's law. Now, we will talk about Henry's law in environmental emergencies, one of the gas laws, but Henry's law is a gas law that describes the solubility of a gas in a liquid, i.e. water in this case. What is the solubility of carbon dioxide in water? I don't want you to calculate it. We're not going to calculate it. I'm just going to give it to you. And it's 0.03. 0.03. All right? So for every millimeter of mercury, okay, every millimeter of mercury of CO2, I get 0.03 milliosmoles per liter of CO2 dissolved. Does that make sense? Right? So very tiny amount, but that's where that 0.03 comes from. Every millimeter of mercury of CO2, 1 millimeter of mercury, out of that millimeter of mercury, 0.03 milliosmoles per liter will actually get into the blood. You guys okay with that? And then the rest of it has to be either converted or attached to something else. So that's where this number comes from, 0.03 times 40. Do you guys see where everything from this equation comes from? All right, so we started here and now we're here. 6.1 is the pKa, carbonic acid. Okay, log base 10, we know that. 24, that is the bicarbonate. 0.03 is a solubility constant for CO2, and the normal value of CO2 in the body is 40. You guys good with that? So let's solve this equation. So what do we do first? Parentheses, right? So basic order operations. So let's do this first. Let's do 0.03 multiplied by 40. What does that give you? Just use your calculators, it's fine. 0.03 multiplied by 40. Say again? 1.2. Should be 1.2. Did you all get that? I want to make sure you all got it. So 0.03 multiplied by 40. You guys okay with that? And that gives us 1.2. And then we have 24 up here. All right. And then we'll put the rest of the equation. So pH equals 6.1 plus log. All right. Good with that? So what do we do next? Well, we need to we haven't taken care of the parentheses yet, right? So let's do that. What is 24 divided by 1.2?
0.83.
0.83. Did you guys get that okay? Is that right?
24 divided by what?
24 divided by 1.2. Or excuse me, 24 divided by 1.2. What'd you get?
20.
Say again?
20.
20, right?
Oh,
You guys,
I put that wrong.
oh wait, you did it wrong, okay. Again, it has to be a number that's close to 24, right? So are you guys okay with that? So let's rewrite this. pH equals 6.1 plus log base 10 of 20. All right. All right, so what gets done next?
Log 10
Good.
times 20.
So I need to take the log, I don't multiply it, I take the log of 20, right? So what is the log base 10 of 20? Do you guys know how to do that on your calculator? So generally it's going to be like 20 log 10. It varies from calculator to calculator.
So put 20 and then just hit the log 10 button.
Yep, that might, if that's how it works for your calculator. What does that give you?
1.3.
1.3. That is in fact the correct answer. So does everybody get that on their calculator?
Redeem.
Indeed, yeah, 1.3. The log base 10 of 20 is 1.3. You guys okay with that? So now let's go ahead and rewrite the equation. 6.1 plus 1.3, and what does that give me? 6 plus 1 is what? 7. 1 plus 0.1 plus 0.3 is, holy cow, the normal, not the range, but the normal pH in the human body is 7.4. Are you guys okay with how we got there? Starting up here at the Henderson Hasselbalch, right? Going through what the Ka is, and we put in all normal values, and all we used were the bicarbonate and the CO2, right? And then of course the the pKa of carbonic acid, right? Which is what? That's a big component. Does that make sense? And guess what? If you have a normal, healthy human being and you measure the pH of their arterial blood, it should be approximately what? 7.4. We see that, right? Time and time again. You guys okay with that? And then we allow a little bit of wiggle room, right? A range of 7.35 to 7.45, but what is right in the middle of that range? 7.4. Does that come as any surprise now that we've worked through all this? Should come as no surprise whatsoever. So does that make sense where we get at pH in the human body? Excellent. So now that we have developed, we've built a foundation, we can actually start talking about analyzing acid-base balance in human beings. But I think this is a good time just to take a little break. Take 10 minutes, we'll come back, and then we'll start that endeavor. Any questions over any of this stuff, or does this make sense? And again, I'm not expecting you to do the math, right? There are some formulas that we will learn a little later on, but you're not going to have to do this. I just wanted to develop how do we get here, right? What's going on underneath the hood, right? So hopefully this will help. This is foundational stuff. All right, get out of here. Take a break.